My name's Samir, and I'm part of the product management team here at MapleSoft. I often get asked my time speaking to users, people like you, helping you to better understand and use both Maple and MapleFlow. I then take your feedback and your feature requests and put them back into the product development process, and then keep development on track to meet your needs. So your feedback is really important to me. Without it, I couldn't actually do my job and make informed decisions about future development. So if you do have one takeaway from this presentation, it should be that I want your input, I want your feature requests, I want to know what you want to do with our software. Your feedback directly influences what we do. MapleFlow is now a year old. We've just launched the second major version, Flow 2022. We'll cover the new features and some of the old favorites later in this webinar. But before that, I wanted to take a diversion and talk about a couple of things first. Flow is fundamentally a math tool. I wanted to discuss how we came up with the name MapleFlow. We actually wanted to pay homage to the heritage of the math engine. MapleFlow is based upon the Maple programming language, which has been under continual development for 35 years, hence the first half of the name. The flow in MapleFlow actually references a psychological concept known as the flow state. You might know it as being in the zone. There's a definition of the flow state here from Wikipedia, but briefly, the flow state is when you're so immersed in your present task that outside distractions simply melt away, your problem-solving skills are firing on all four cylinders, and you just feel great and have a sense of accomplishment when you complete your task. We wanted to bottle that up and give it to you in a math tool. To help us develop and design MapleFlow, we needed to understand and appreciate the characteristics of engineering calculations, how people feel most comfortable doing an analysis and using software, and how calculations should be presented and deployed. And that's what we'll explore next, the rules and principles that have helped guide the development of MapleFlow. The influences actually stem from three different sources. The characteristic of the actual equations, the engineering math. Then we'll cover the human factor. We'll discuss the engineer actually doing the calculations. And finally, we'll talk about the requirements and goals of the engineering enterprise, the sponsoring body that actually pays the engineer to do that work. We'll discuss each of these in turn. First of all, let's talk about the equations. So engineering equations are actually derived from physical laws. That groundwork could be laid by a heat and mass balance or some application of thermodynamics or Kirchhoff's current and voltage laws. Generally, you need to go to university to learn about these concepts. However, when you work professionally, you'll often find that most of the time some very clever people have already done the heavy lifting and have used these physical laws to model concrete retaining walls, heat exchangers, or the safe working distance to prevent an electrical arc flash. The results are available in design guides such as the International Building Code or the IEEE design standards. And many engineers simply take these standardized approaches in design guides and apply them to new applications, new situations. Now, the parameters in those equations are inherently dimensional. Lengths, forces, voltages, masses, energies, all have dimensions. The dimensions matter, and you have to get them right. In fact, the dimension is as much a part of the parameter as is its numerical value and should really be carried along with it. We've all heard stories about what happens when you get the units wrong. One of the most spectacular disasters was the Mars Climate Orbiter disaster in 1999. As far as I recall, one software component generated results in US customary units, while another software component expected those same results in metric units. And as you know, there's a big difference between pounds for seconds and Newton seconds. There were rocket scientists working on that for NASA, but you don't have to be a rocket scientist to make errors with units. Anyone using a spreadsheet can make a unit conversion or a consistency error. In my time, I've seen lots of engineering spreadsheets come across my desk. And of course, Excel doesn't understand dimensions, it doesn't perform unit conversion factors, and it doesn't ensure the dimensional consistency of equations. That just leaves the door open for expensive unit errors. Now, equations carry context, and that context, that meaning is important. Let's say that you just see this number divorced of any meaning or context, either written down on a piece of paper or in a spreadsheet. So what does that number mean? What does it represent? How is it calculated or generated? And quite often that's all we see in a spreadsheet unless you drill down into the cell. There might be a few context clues in the form of text or the title of the spreadsheet, but invariably there will be some detective work involved if you want to understand the provenance of that equation. Here we have the same number given context, clarity, and meaning simply by making the equations explicit. You know that this is the area of a circle. You could infer that somebody measured the diameter with a pair of calipers or found the value in the table. The units are also explicit. This type of presentation is far more meaningful. Now, that actually points to a broader question of how calculation should be presented to maximally convey meaning. There's the concept of the engineer's notebook, a bound pad of paper filled with equations and notes. And for this, I really like referencing the calculation notebooks of one of my personal engineering icons, a Victorian engineer called Isambard Kingdom Brunel. He worked in the 1800s in the UK. He designed bridges, steamships, and railway stations with intellectual flair, diagrams he drew himself, and calculations he did by hand. He did all of this in his engineering notebooks. His original calculation notebooks are still preserved at the University of Bristol. And what you have on the right-hand side is an example of one of his calculation notebooks. It actually documents some of the calculations he needed to design the Clifton Suspension Bridge, which opened in 1864. He used whatever tools were available at the time to do his calculations, but his paper notebooks were the center of his technical desktop. That's where he did his calculations, wrote down his notes, and drew his diagrams. And this is still meaningful. This is still understandable. Now, sometimes all you need are basic arithmetic operations to do your engineering analysis. It might be nothing more complicated than addition, subtractions, multiplications, divisions, peppered with the occasional log or trig function. But sometimes your analysis requires a little more mathematical grunt. And by that, I mean something that you can't easily do in a spreadsheet or on paper. You might need an algorithm to solve an algebraic or a differential equation numerically. You might need to do an FFT on some data, or you might want to do some regression or curve fitting. You might also need state-dependent thermodynamic quantities or tools to visualize the frequency response of linear systems, such as phase and magnitude plots. That really needs a robust, broad math engine with higher level math functions than you get in a spreadsheet. Now, let's move on to the human factor. This was an important factor in helping us design Maple Flow. An engineer sits firmly in the middle of the problem-solving process. The way most engineers solve math-based problems is really very loosely structured, and some would say uncharitably haphazard. An engineer might know where they're heading, but they don't know how to get there or where to start because they don't have all of the steps planned out in computational detail. They progressively refine their analysis, correcting mistakes as they go along. Problem-solving tools like MapleFlow need to be designed to support that human-centered workflow. People also have a limited amount of short-term working memory. So if you're doing anything non-trivial, you need to make notes as you're working. Now, it's true that people like short-term gratification, and that's not necessarily a bad thing if that blast of feel-good neurochemicals is a reward for completing a discrete task and doing it well. So software tools need to feel good to use. And of course, people get frustrated. That might be because of some ambiguity in a reference text or because of the mental overhead needed to use a complex math tool. And quite often that you'll need to work through that frustration to complete your task, but that stress, that frustration will really make it less likely that you'll willingly do similar work in the future. So math tools need to be designed to be as simple to use as possible, as intuitive as possible. Now, not all engineers are the same. There are many ways of slicing and dicing the engineering community into recognizable groups. One way is to recognize the differences between research engineers and design engineers. Research engineers, I find, tend to have more in common with mathematicians than engineers. They're deriving equations from first principles physics or researching mathematical methods to solve complex engineering problems. These are the engineers that might be using tools such as MATLAB, Mathematica, or the Python programming language. Research engineers are also the traditional target market for Maple. Then we have a broader swath of engineers who we can call design engineers. Their mathematical needs are rather more prosaic. They're probably more interested in the application of math rather than the math itself. Their equations or methods are probably already well established in design guides or engineering textbooks. They're on a very well-trodden path. They just need an environment to click all the blocks together in the right order with the least cognitive overhead. The tools for these guys tend to be tools like Excel or MathGAD, and this is actually the target market for MapleFlow. Now, of course, there is some overlap between these two groups, research engineers and design engineers, but by and large, this distinction can be made. So the next influencing factor that guided how we develop MapleFlow is how a calculation is used across an engineering organization. Now, an engineer simply doesn't just do an analysis, then puts the result in a drawer. That calculation might be a shortcut to faster analysis for the next problem for their colleagues. Engineers have a tendency to automate and mechanize some part of their job to make themselves and in turn their group more efficient. And in parallel, that equation could be used to make an informed decision about a product design for their company. That analysis might have to be shared with clients or a colleague. It has to be archived and managed in some kind of documentation system. And that might just be a shared network folder, or it could be a complete PLM system. If the engineer leaves, storing the calculation in a structured, easily accessible form means that a new employee doesn't have to reinvent the wheel, but can carry on where the previous guy left off. If that process of managing calculations, storing calculations and archiving them is done properly, that means the engineering enterprise, the company, saves time and money and increases overall employee efficiency. And for highly regulated industries such as structural or nuclear engineering, Increased efficiency ultimately leads to greater regulatory compliance. Now, we've just discussed the factors and principles that have influenced the design of MapleFlow. I'm now going to recap and summarize what we've just discussed, but I'll recast everything as a guide for you to decide if MapleFlow is aligned with your needs. So MapleFlow is the right tool for you if your equations mean something real. That might mean your equations mean something as simple as the area of a circle, or a heat transfer coefficient, or the strength factor for a bulk group. You might need to evaluate those equations in sequence to describe a model or determine the parameters of a design. The parameters in your equations have units and dimensions, and you need to convert between different sets of units. Your mathematical needs aren't really overly complex, but you might need to do some moderate number crunching or symbolic math or generate some plots. And you need something more than Excel to do that. You like to progressively refine your work because you don't have all of the steps planned out in advance. And you want to build up a body of readable calculations that you can use as a shortcut for future analysis. If you recognize some or most of these elements in the work you do, then MapleFlow is worth investigating. Now, these are some of the features that we've engineered in MapleFlow to support design engineers in doing their mathematical work. And you'll see many of these in action when I demo the product. So it's a free-form tool for doing engineering calculations and creating documentation. You can place your work, your math, text, plots, and images anywhere on a canvas and move them into position. The design of MapleFlow means that it's easy to progressively refine your work. Because MapleFlow is based upon a high-level math engine, it means that you have many different mathematical tools covering virtually every area of engineering computation. And there are many documentation features such as sections, font and paragraph styles, and so on. So moving on to MapleFlow 2022, which we released a couple of weeks ago. And these are the new features that you'll see in the product. I'll show you some of these in action when I demo the product in a few minutes. But previously, MapleFlow was an add-on to Maple. However, MapleFlow 2022 is now standalone and a separate Maple install is not required. We also have an all-new help system. And these help pages are actually pretty good. The pages look like flow sheets. You can copy and paste from them. You can open up these help pages and as worksheets and start working with them straight away. We have a new options menu, which allows you to define what you want to do with hyperlinked worksheets, whether you want them opened up in new windows or new tabs. You can change the background color of math containers. That means you can highlight specific groups of containers or draw attention to your results just with some subtle coloring. And we've made some other improvements as well. What I'd like to do now is actually switch into Flow and actually show you the product in action. I'll cover some of the features that we introduced over the last year, and I'll also cover some of the features that we introduced in Flow 2022. So this is the home screen for MapleFlow. There are 3 buttons, one to create a new canvas, another to a series of tutorials, and the third is to an application gallery. The application gallery is a library of applications across a number of domains where we feel MapleFlow has some value and where we have users. There are applications for aerospace engineering, chemical engineering, chemistry, electrical engineering, hydraulics, structural engineering, and so on. For now, what I'm going to do is fire up the civil and structural engineering section, and I'm going to load this application. So this is just a pre-engineered Mapleflow application. At the top, we have a title and a description of the problem. If I scroll down, you can see some text and some parameter definitions. So here I'm defining a yield stress and the modulus of elasticity. And you can see that I have units associated with them. If I scroll down even more, you can see I have equations in natural math notation with overline division, superscripts for powers, Greek letters, and so on. My results of units. So this result is given in units of millimeters, but if I want to rescale this to another unit, that's simple enough to do. All I do is click on the result, open up the context panel on the right-hand side, and type in my desired unit, let's say inch. If I press enter, Mapleflow rescales the result 2 inches. A canvas updates automatically if you make any changes. So if I change this value here and I press enter, that change cascades down the length of my Mapleflow canvas. And if you pay careful attention, the number at the bottom changed. Change that again. There, you can see the result of the bottom changing. So a canvas is always up to date. That is, unless you disable automatic calculation. So let me go back to the start page and open up a new canvas. You can click and place the grid cursor anywhere on your canvas. At any point, I can start doing math. I can start typing notes and text. I can move things about just by clicking and dragging, or if I move this cursor into a math container, I can shift things about with the arrow keys on my keyboard. So if you don't like taking your hands off the keyboard, you don't have to. I can also define parameters and use those parameters in my analyses. And of course, if I change the values of X and Y, that change cascades down the length of my Mapleflow canvas and the results update. So a canvas reads from left to right, top to bottom. So if I take this definition of X and move it to this point, well, this equation doesn't know what the value of X is anymore. So it's left as an unassigned name. Move it back up. There we go. So Mapleflow is based upon the Maple programming language. That means you can use nearly all of the tools, functions, and features in the Mapleflow programming language to do your work. So if you wanted to, you could use this function to solve an equation or a group of equations. You could use these tools to extract thermodynamic data. So here we're extracting the density of water at a temperature of 320 Kelvin, let's say a pressure of 1 atmosphere. So here's something that you can do. If I define row as the result of this command, quite often I don't really want to see this big command. I only want to see the name. and the result. What I can do is right-click on this math container and select Hide Commands. The bit in the middle disappears. It's still there under the hood, but this looks a lot cleaner. So you can also structure your worksheet with sections. So if I grab a selection box around a group of results and I go to Insert Section, that places two horizontal lines across the length of my canvas. I can actually drag these up and down to include more or less of my work, and I can expand or contract the section. If the section is contracted, if it's collapsed, that content is still there. It can still be used in any further mathematical work, but it's hidden from view. So one major feature that we've introduced in MapleFlow 2022 is the new help system. We still have the user manual, which was available in prior versions of Flow. So this introduces you to the basic operation of the product, the navigation of the user interface. But if you want some help on commands, syntax, functions, if you go to MapleFlow Help, a help browser pops up on screen. You can browse for topics, click on results, and once you get to a command that you like the look of, you can actually copy and paste it into your own work. So if I grab this, I can copy it into the clipboard and paste it into my canvas. Oops. Let me remove that definition of Y. And now this is usable in my MapleFlow canvas. So I could take the zero pole gain model and create a magnitude plot from this. So one of the resources that we've been working on to coincide with the launch of Flow 2022 is the new application center. So if you go to our website and go to Support and Resources and the Maple Application Center, and then you hover over Products and you select MapleFlow, here we have about 120, 130 Maple applications across a number of domains. These can be freely downloaded. So for example, I could download this application and load it in MapleFlow. So there's lots of content for you to play about with. Let me close down some of these worksheets. So to help you create structured groups of worksheets, people often use hyperlinks. In the new options menu, which you can get if you click on the gear icon here, we have options which allow you to specify whether you want hyperlinks to open up in a new tab or a new window. and you can apply that option to this specific session or to all future sessions of MapleFlow. So that covers nearly everything I wanted to talk about today. If you want to learn more, then I do encourage you to go to our website. There's lots of information there. There are links to the MapleFlow Application Center. And there's also a window which allows you, button which allows you to download a free trial.